Hello, and welcome back to Physics 141 Classical Electromagnetism 1. So, this will be the last topic for the first chapter on electrostatics. So, before we start, let's review the topics or the concepts that we need for this final lesson. So, in the previous lesson, we have calculated the energy of uh, a discrete charge distribution, which is just equivalent to the work done in moving or in assembling the charges. So for a single charge, Q, if you want to move it up at a point from infinity, if you want to move it at a point where the potential is V, then the work done in doing that is Q times V. So we also have discussed about the potential difference, which is just related to the electric field, E dot dl. So for this chapter, or sorry, lesson rather, we will be discussing about capacitors, how to find the capacitance of the capacitor, its main property, and its the energy stored in a capacitor. So a capacitor is basically just parallel sheets of opposite charges. So you have two conductors, two conducting sheets of charge. One sheet has a total positive charge Q, and the other sheet has a total charge of negative Q. And these two sheets are parallel with each other. They're equidistant. All points are equidistant, and they are maintained at a potential difference of V AB. So we have learned from Coulomb's law that the electric field is proportional to charge, and that electric potential is also proportional to charge. And the proportionality constant relating the electric potential, or potential difference rather, and total charge Q is what we call the capacitance. So it relates Q and the potential difference VAB. So basically this is the capacitance. The capacitance is actually just a measure of how much electric potential energy that can be stored within the field of a capacitor. So you have discussed in your Physics 41 that the electric potential energy in a capacitor is actually stored within the field, within the electric field. So you can also think of the capacitor as storing charge, because charges is stored in the surface or on the surface of the capacitor. So it's actually pretty similar to a battery. A battery stores energy, or a battery stores charge, but the nature of the energies is what's what's different between a capacitor and a battery. A capacitor stores electric potential energy. A battery stores chemical or electrochemical potential energy. So the simplest design of a capacitor is a parallel plate capacitor. So basically you just have two sheets of charge separated by a certain distance d, and a potential maintained at a potential difference v. So for instance, we are asked to find the capacitance of a parallel plate capacitor. So basically this is the simplest design of a capacitor. You have two sheets of charge. One is positive Q, one has a total charge of negative Q, and both have the same area, surface area A, and are separated a distance d, and maintained at a potential difference VAB. So here we'll let the points in the negative sheet as A, and the points in the positive sheet as points B. Okay. So let's first start with the potential difference. Let's first find what is the potential difference between the two plates of a parallel plate capacitor. So we use our equation, negative E dot dl, from A to B. Now, we can let this axis as our z-axis, and we can let our negative plate to be at z is equal to 0, and our positive plate to be at z is equal to d. So they have a distance d. And if you will recall, in when we discuss about the sheets of charge, so the electric field between two sheets of charge, a positive and a negative sheet of charge, between them is actually just sigma over epsilon naught. And the direction of the electric field is from the positive, of course, towards the negative sheet. So that's the direction of the field, from the positive, so downwards. So the direction of the electric field is actually along the negative z axis. So using those information, our electric field is sigma over epsilon naught. Its direction is negative z hat. And our dl is just so the line from A to B, this axis is the z-axis, so therefore our dl is dz z hat. So this is just a pretty straightforward integral. Sigma is a constant, epsilon naught is a constant, z hat, that z hat is just equal to 1. So we will have integral of dz from 0 to d, and that integral will give you d. So your answer will be sigma d over epsilon naught. Now, sigma is just the charge density. It's just the total charge over the total area. In this case, sigma is q over a. So in this case, sigma is the magnitude of the surface charge density, q over a. So therefore, knowing that this is the potential difference, it's proportional actually to q times the distance and inversely proportional to the area. So we use that value to solve for the capacitance. So it's just q over the potential difference, VAB, and simplifying we get the potential, the potential or capacitance rather of a parallel plate capacitor. So you will notice that the capacitance of a parallel plate capacitor is directly proportional to the surface area of the plates, and it's inversely proportional to the distance. So if you want to make a parallel plate capacitor with a very large capacitance, so it has a very large it can store larger amounts of potential energy or charge, then you have to increase the surface area, and you have to make the distance between the plates as small as possible. So actually that's the basic ways on how to increase the capacitance of a capacitor. Increase the surface area, decrease the separation distance of the plates. So there are actually many types of capacitors depending on symmetry. So you have spherical capacitors, you have cylindrical capacitors. So for instance, a spherical capacitor will look like this. So this is a cross section of a spherical capacitors. So you have two spherical conductors. For instance, the inner spherical conducting shell has a total charge of negative q, and the outer spherical conducting shell has a charge of positive q. The radius of the inner shell is a. The radius of the outer shell is b. So how do you find the capacitance of a spherical capacitor? So similar with our previous example, we start by finding the potential difference between the two conducting shells. So the electric field here, since this is a negative charge, meaning the electric field will be directed towards the negative charge, or inwards, radially inwards. So this direction of the field is along the negative r hat direction, or inwards. So we have already solved for the electric field outside of a conducting sphere. It's basically just 1 over 4 pi kq over r squared, and in this case the direction is inwards, or negative r hat. our dr here, since our dr from A to B is just the r axis, so it's just dr r hat. So this is just a constant, q is a constant, r hat, that r hat will give you 1. So inside the integral, the remaining term inside the integral will just be dr over r squared. And of course, the integral of that is negative 1 over r. And you evaluate that from A to B, and you get this potential difference. So this is the potential difference, the voltage between the positive conducting shell and the negative conducting spherical shell. So using the capacitance as charge per unit potential difference, you substitute the results for the potential difference, and you get the capacitance for a spherical capacitor. So you will notice that it depends only on the radius of the shells A and B. And similarly, B minus A here is the separation distance. So B minus A is this length here, the separation distance between the two shells. And if this separation distance is very, very small, then your capacitance will become very, very large, similar with the parallel plate capacitor. So as an exercise, I will leave this to you. So try to find the capacitance of a cylindrical capacitor. Just follow the steps in the previous two problems. Find the potential difference between the two cylindrical shells first, and then solve for the capacitance by using the formula Q over V. And you will get this answer. So the capacitance for a cylindrical capacitor depends linearly, directly on the length of the capacitor. So the longer the capacitor, cylindrical capacitor, the larger the capacitance, and inversely proportional of the natural logarithm of B over A. Okay, so how do you charge a capacitor? So for instance, you have a parallel plate capacitor. In order to charge it, so suppose it's uncharged, it has no charge Q on either of the plates. Then you connect it to a source of EMF, such as a battery, for instance. So this is our symbol for a source of EMF, or source of voltage, if you like. So this source of EMF will give your capacitance there will be a current, at an instantaneous current, a time-dependent current. And from our equation for capacitance, the relationship between V and Q is just this one. So this is the instantaneous voltage of our capacitor, and it's related to the instantaneous charge over the capacitance. So of course, the final voltage of your capacitor will be VAB, and the final charge of your capacitor will be a capital Q. So at the start, they're both 0. So from our definition for the work done in moving a charge Q at a point where the potential is V, so work is just Q times V. Okay, so the differential work there will just be V dQ, and since V is just Q over C, so we replace V by Q over C here, and we'll have and integrate this one to get the work done. So the work needed in charging a capacitor will just be equivalent to the energy stored in the capacitor. So the energy that you expend in charging the capacitor will become the potential energy, or the energy stored inside a capacitor. So if you integrate this one, Q dQ, from 0 to a final value, capital Q, the final charge, then you will get Q squared over 2. The integral of this is Q squared over 2. So you will get Q squared over 2C. This is the work done in charging the capacitor, and this is also the, sorry, what happened? This is also the energy stored inside your capacitor. So that's the end of the first chapter, the chapter on electrostatics. So our next chapter will be devoted to special techniques in finding or in solving the Laplace equation. So if you solve the Laplace equation, meaning you solve for the potential, electric potential. So the potential is one of the key elements in electrostatics. If you know the potential, you can solve for the electric field and you can solve for the charge density. So chapter 2 will all be about special techniques in solving the Laplace equation. So that's it for this chapter, and wait for announcements for your problem sets and your chapter exam. So thank you, and I will see you next chapter.